Okay, hello and welcome to my channel. Today, we're gonna take a look at an example for you to apply to exercises in the stationary states chapter. So we're just gonna take a look at the most simple, the simplest one, which is our good old friend, the particle on the circle. Okay, so particle on a circle. And let's draw a circle here. It's gonna rotate. Right, start here. All right. So, as I said before, this guy, when you go a full loop, is gonna come back to the same point, and we can draw that out. That's something like this. All right, and you get that x plus L is equal to x. Therefore, the psi of L is equal to the psi of 0. Psi of x plus L is equal to psi of x. All right, so these are what we got, and considering that it is just spinning around in a circle, our potential is still 0. All right, and let's start with our time-independent Schrodinger equation, which is Hamiltonian on psi is equal to E on psi, and you expand this. This guy is also this E psi. You take this part and you throw it over there, you would get, well, just the second derivative would equal to 2me over h bar squared psi. Okay, and here you can see something familiar appearing already. Oh my gosh. And this guy, you can take this to be k. Therefore, your equation becomes something like this. And as you remember, the solution for this is the exponential, so e to the ikx, right? Here you can get that your psi is an exponential of ikx. Right, now we're going to use these properties right here. So, okay, I think I might have forgotten the minus sign. This is minus k. So, yeah, minus k. So this would be plus. Right. Energy positive. So, this, take a look at that. E to the ikx would be the same as e to the ikx plus L. What would that imply? That would imply that, well, ikl would equal to 0, or you can say that e to the ikl equal to 1. And what, okay, I will write that down first. This would give you e to the ikl would have to equal to 1, since this part has to be equal to 0. And what would give you 0 from this? Well, the KL here would have to equal to a multiplet of 2 pi, right? That is just some textbook stuff, so I won't be going back to that now. This would need to be a multiplet of 2 pi. From here, you get that your K is equal to 2 pi n over L. And we got our K. Now we can, well, consequently get our P as well. So from here, get that your P just K times H bar. Remember that? Get your P, and what we want ultimately would be to get our energy, right? So the energy would, okay, find somewhere to write that. Okay, there. the energy would be, well, it's kind of hard to see, would be equal to P squared over 2m. That is 2 pi squared h squared n squared over, I think, 2m, yeah, no, ml squared. ml squared. All right. So you got your energy now. Now we would want to normalize your eigenstates, right? Okay, so I think I got confused a little bit, but these are, well, these are eigens. No, these are stationary states, and what you get is an energy eigenvalue. All right, so all of these, the psi, just add an n to it to signify that it is a stationary state. I forgot to do that, apparently. So now your psi would take the form normalization coefficient, and this guy, the exponential part. Okay, so we already know that that has to be, no, we take that equal to 1, so your psi would only equal to a. Now with that, you do the normalization stuff. Just you integrate it, right, equal to 1 from 0 to L, because it would only hop periodically as L, so to L, 2L, 3L. So this is an integral from 0 to L. And what would you get from that? Well, okay, this is getting really hard to see. You would get that your A is equal to 1 over root of L. As we used before, the form of a wave function on a circle would equal to, well, 1 over root L, the exponential part. We use that when we talk about the completeness of the wave function. Okay, so there you go. You got your stationary state, and a circle would be 1 over root L, and this, the exponential part. And from this, you can get the, okay, I need to erase something. You would get the time evolution of the state. So your psi of x t would be that the time evolution, here's the exponential of minus iet over h bar from n to minus infinity to infinity. Right, now we're gonna consider your psi 0 of x. This guy would just equal to 1 over root L. When you, and then you consider next is psi 1, psi 2, you would see that your energy, whether it's a plus or a minus in the end, it would equal to each other. So you continue on. Your E, I would write this as, your E plus would be the same as your E minus. Okay, E plus would be the same as E minus. Okay, and this signifies a degeneracy. So you can say that psi, suppose it's continue to k, all right? So we can say that psi k and psi minus k are degenerate. So meaning that they have the same energy, and that would apply for any periodic psi. So you get that with any periodic psi, you can write this as that. And let's talk about the property of the energy eigenstate of these psi. All right, so with these, you would have the property that is your psi of k plus, running out of space so much. Your psi of k plus your psi minus k, that would be proportional to the cosine kx, and the minus would be proportional to the sine. And these are the property of the energy eigenstates of these sort of wave function. All right, and that's it for today. Goodbye.